Hello everyone. Today I am going to discuss one problem of CSES problem set, which is minimum rotation, and the string algorithm required to solve this problem. So this problem is a bit hard one, but the algorithm behind this problem is quite interesting. So I will suggest you to watch this video and process this video slowly, and if needed, see this multiple times. Okay. So let's go through the problem. So what is the problem? We are given a rotation. We are given a string S, and what we have to find, we have to find the lexicographically minimum rotation of a string. So what are the lexicographical rotations? So let's say we have this string ACAB. So if we rotate this string, there are multiple different strings are formed. So let's right rotate this one times. So if we right rotate this one time, this B will come first. So the string will be BACA. Now again right rotate this string, it will be ABAC, and again right rotate this, it will be CABA. Okay, and again if we again right rotate this, it will again become ACAB. So there are four right rotations. The length of the string is 4, so there are four right rotations. So among these rotations, what is the smallest lexicographically smallest string we have to find? So among these four, this is the smallest one. So this should be the answer. Okay, ABAC is the answer. Okay, so the problem seems quite straightforward if we try to go by the brute force order of n square solution, where we find every possible lexicographical part, lexicographical string. So if we find the first lexicographical string, first rotation is with k value 0, and first one right rotation with k equals to 1 means we are doing k right rotation. So this is k equals to 0, this is k equals to 1, this is k equals to 2, and this is k equals to 3. Okay, so we are doing for different values of k, we are finding the strings, and after that, if we find the maximum of these strings, we will get the desired answer. But this time complexity of this algorithm is nothing but order of n square. Okay, order of n square, because there are n characters in the string and we have n right rotations. So overall time complexity is order of n square. So the brute force approach will fail. Now, now comes the interesting part, how we will solve this problem in linear time complexity. So from order of n time complexity, we will reduce the time complexity to order of n. So this is important, and one important algorithm, an interesting algorithm comes here, which is called Duval's Lyndon factorization. There are other algorithms also, Booth's algorithm, but I have read this algorithm only, so I will discuss this Duval's Lyndon factorization. Okay, uh, so I will jump to the C, uh, CP algorithms page for this algorithm, which is Lyndon factorization. I'll provide the link of the article in the description box. You can check that out. So let's go through this article once. So a string is called simple if it is strictly smaller than all of its non-trivial suffixes. So a string will be called simple if it is lesser than all of its suffixes. Okay, so AAB, this string is simple because if we take all the suffixes B, BA and AAB, B, AB and AAB, this one comes to seems to be smallest. But let's say we have something like ABAA. Okay, we have something like ABAA. Now, this string is not a simple string because there is a suffix of length to A, which is smaller than the entire string. Okay, so that's why this is simple, but this is not. Okay, so that's the definition of a simple string. Now, what Lyndon factorization does is that it divides a string S into some simple simple strings. Okay, simple strings, such that the first string is greater than equals to the second string, like that. Okay, W1 greater than equals to W2, greater than equals to the next one. Okay, so let's try to figure out what could be the Lyndon factorization of the given string ABA. Okay, let's go through the ABA first. Okay, we'll go through multiple examples to make this clear. Okay, so ABA, it would be divided into multiple simple strings. Okay, so what are those strings? So the first string I think is AB. The first string is AB, and the next string is A, and the next string is A. So there are three strings here: AB, A, and A. I hope you got it. Get it? So these are the Lyndon factorization of the given string ABAA. Okay, I will take some break once. So let's explain the next part. This part is a bit difficult. So it is Duval's algorithm. So Duval's algorithm, what it says is that it gives the definition of pre-simple. Another term, pre-simple. Pre-simple is a simple string only, but what it has is that the last part. The last part is the prefix of the given string. Okay. So here T is WW and W bar, where W is a simple string and W bar is a prefix of W, possibly empty. So in any simple string is also a pre-simple string. Okay. So what does Duval's algorithm says that it divides the any string S into three substrings S1, S2, and S3. So S1 is already found. The Lyndon factorization of S1 is already found and finalized. S2 is pre-simple, and S3 is completely untouched. Okay. Now here comes the this part. So this part is the transitions we are doing with the steps. Okay. So let me take one example. You will understand it more clearly. Okay. So let's take this example. We have BBC. We have BBC. Okay. Okay. BBC, and BBA. We have, let's say, this string. Okay. Let's if we go to this algorithm and the code, we have some value of I. So let's ignore I now. So initially, let's say j is at the zeroth position, j is at the zeroth position, and k is at the first position. Okay, let's say j is at the zeroth position and k is at the first position. Now, initially S2 is empty. Now, if Sj equals to Sk, in this case, then adding the symbol Sj to S2 does not violate its pre-simplicity. Oh, why? Because BB is simple and also B is part of the prefix. Okay, so that's why BB is pre-simple. In that case, if Sj equals to Sk, we will just increment the value of both J and K. So let's say our K is at the bottom, and let's say J is at the top. Okay, so Sj is equals to Sk, so we'll increment the value of both J pointer and the K pointer. Okay, now here comes where Sj is greater than Sk. Here the second condition comes, Sj greater than Sk. Here the string S2 plus Sj becomes simple. Okay, S2 plus Sj becomes simple, but it is not pre-simple because it is not part of the prefix. Okay, so it is not simple. So in that case, we'll just reset the value of this K pointer. We'll just take reset the value of this K pointer and mark it at the ith position or the initial position, you can say. So we'll K will be moved to here and J will be moved to here. Now again the comparison starts. Okay. Now again Sj equals to Sk, so this will be incremented here. Uh, Again Sj is equals to Sk, J is incremented to here. Now Sj is equals to Sk, so this K will be moved forward and J will also be moved forward. Now this time Sk is C and Sj is also C, so this will be K will be moved forward and J will also be moved forward. Okay. Now mm, again Sk equals to Sj, so we'll move the J pointer forward and K pointer also to the next string. Okay. Now this is also matching, so J pointer now will move to A, but the K pointer will move to C. Okay. Here comes the third point. Okay, here comes the third point. If Sj less than Sk, this means the string S2 plus Sj is no longer pre-simple. S2 plus Sj is no longer pre-simple, and also it is no longer simple because we have encountered something, some A. We have encountered some string A, which violates the simplicity of the string, because if we take the suffix from this A, because what let's remember the definition of simple. The definition of simple string means that any suffix of the given string should be greater than the lexicographically greater than the current string. But if we take any substring from this A, uh, this the suffix will be greater than the sorry lesser than the lexicographically lesser than the current string. That's why in that case we have to stop this iteration. We have to stop this iteration. The simple string will have the length of j minus k, and the next iteration will start again for the remaining s2. So here j is our k is here and j is here. So j minus k is equals to 3. Okay. So we'll take all the substrings starting from the first position or the ith position. Here I comes. So I will be untouched in this iteration, and I will be initially pointed to k. Okay. So we will take length 3 substrings from these given strings until I is less than equals to k. So we'll take this BBC and this BBC. So BBC and this BBC will be pushed into the Lyndon factorization. So the Lyndon factorization of the given string will be nothing but BBC, BBC, and we have to do the Lyndon factorization again for this BBA. So the Lyndon factorization of the BBA will be nothing but B, B, and A. Okay, so this will be BBC. So BBC, BBC, B, B, and A. So there are 5 Lyndon factors. Okay, here I hope you got how we are doing the Lyndon factorization. Uh, you might rewatch the video and please try to read what this SJ and SK means. So why we are taking the length of J minus K? Because when we are resetting the value of K, we are figuring out that the last J minus K values, after the last resetting, the last J minus K values, this J minus K values will be same. This J minus K value and this J minus K value will be same. That's why we are taking the substring of J minus K from I, and again the substring of J minus K I again. Okay, so let's jump into the code. So here I is initialized with 0. So while I less than n, we are initializing K with I and J with I plus 1. In the inner loop, in this loop, I is not touched. Okay, that's why I have not taken I in my explanation also. So if SK less than equals to SJ, because if SJ is less than SK, we are breaking. So if SK, while J less than N and SK less than equals to SJ, so this part comes. If SK is less than SJ, then we are saying that this is not a simple string currently. Okay, sorry, this is a simple string currently, but this is not a pre-simple. That's why we are marking k as I again, and otherwise we are incrementing the value of k because the pre-simple string continues. Okay, now is we are doing k plus plus, and at the each iteration we are doing j plus plus. Okay, now after this iteration is done, we have some value of j and k. So we are taking j minus k length portions. These positions will be same, BBC and BBC. This will be same. So that's why we are doing, while I less than equals to k, we are doing factorization dot pushback is dot substring of I comma j minus k. So from I, we are taking chunks of length j minus k and incrementing the value of I to j minus k. We will continue this process until I less than equals to k. Okay, if I greater than k, we will just break. Okay, and at the end we are returning the factorization. Okay, the complexity of this is order of n. I have not I have just vaguely understand how the complexity is changing, but I have not really uh, read about the time complexity and gone deeper into the analysis of the time complexity. But overall, the time complexity is around order of n. So that's how we are factorizing the any given string in to Lyndon factors using Duval's algorithm. But let's jump back to our original problem. What is the original problem? The original problem is minimal rotation. Okay, this is also written here. The problem is also written here, finding the smallest cyclic shift. Uh, so what are they doing here? We are instead of taking, let's take the original example ACAB. So instead of taking the original string only and making its Lyndon factors, what we are taking? We are taking this string and making it double. So AC, we have something like ACAB, right? So we are taking ACAB and appending ACAB again. Okay, appending ACAB again. Now we'll just do Lyndon factorization of it. Lyndon factorization of it. I am not doing the Lyndon factorization, but it will be something like I think AC. I think this will be something like AC, AB, and yeah, AC, AB, and then again AC, and then AB. I think that only. So we have to take the last Lyndon factor whose starting value. Let's say this is S1 and D1, and this is, let's say this is S2 and E2. So we have to take the S2 value, S2, which is less than n. Okay, S2 less than n. Okay, then we can say that from this S2 to E2, this will be the smallest prefix of the cyclic shifts. So AB is the smallest prefix of the cyclic shifts. So that's why we'll take the in length substring from this. So S2 to S2 plus n. We take S2 to S2 plus n. We'll get our desired answer. So we have to find the largest S2 which is less than n. S2 being the Si being the Lyndon factorization, start of the Lyndon factorization, and we'll take S2 to S2 plus n our desired answer. So let's jump into the code. So here, this part is just Lyndon factorization. Instead of pushing the substring to the Lyndon factors, I am pushing the start indexes of the Lyndon factors. So that's why we are doing answer dot pushback I, and I is incremented to j minus k. So after that, I am taking lower bound in the ls and lower bound of n. Okay. So lower bound of n means it will give us something like n to n plus something like n to 2n. So after that, we are decrementing the pointer. If we decrement the pointer PTR was pointing to something like n to 2n. If we decrement the pointer, it will obviously point to something which is less than n, and which is the highest. So that's why we are decrementing the pointer, and we are taking uh, in length substring from the given index. Okay. I hope you got my explanation. I will provide the link of the code in the description box. Also, share the Lyndon factorization link in the description box as well. Uh, if you have any doubt in any part of the video, you can rewatch the video or read the entire dual algorithm and Lyndon factorization from the CP algorithm. If you still have any specific doubt, you can always ask in the comment section. I will try to reply each and every comment. If you find this video helpful, also the series helpful, where I am just explaining different string algorithm concepts with CSES problems. Please like the video, subscribe to the channel, and also share among your peers. Thank you.